Let's take a look at this classic circular motion problem, the loop. Here we have our roller coaster car. It starts at point A. It moves into the loop at point B. It's at the bottom of the loop, about to go around in a circle. It works its way up and around. At point C, it's at the very top of the loop. Then at point D, it's halfway down. And then it comes out of the loop and continues on at point E. We're going to take a look at the 3 points in the middle when it's in circular motion. Circular motion problems are just dynamics problems. Newton's law problems, F equals ma, whatever you want to call them. So we use our dynamics lens, and this is a special case when something's moving in a circular path because we know what the acceleration in the radial direction has to be. It has to be v squared over r. Let's start with our roller coaster car at point B. And we'll assume it's on the circular part of the track there and it's turning up and it has centripetal acceleration. What's the first thing we do for a dynamics problem? Draw a free body diagram. There's my roller coaster car. What's touching the roller coaster car? The track. And the track can push up with a normal force. That's the only thing touching the car. What's reaching in from a distance and pulling down? Gravity. Now we say sum of the forces in the radial direction has to be m times a centripetal. This is a vector equation, so we need to pick a positive direction. I'll tell you my hint. Always pick the direction of the acceleration to be positive. That way you don't accidentally forget a minus sign. So what direction is the acceleration in this case? It's circular motion, so it's toward the center of the circle. If I indicate the direction of the acceleration here, that's the direction I want to be positive. Radially inward, toward the center of the circle, in the direction of the acceleration. And I'll tell you why I like to do that. Because let's take a look at the next step here for our equation. The next step is to fill in what these things are. The net force in the radial direction. Well, I have two forces in that direction. I have a normal force that points in my positive direction. And I have the weight that points in the negative direction. I add those up and I get m times the centripetal acceleration, v squared over r. Well, v squared over r will never be negative when you put the numbers in there. So if I picked down as my positive direction and I'm plugging in my acceleration here, I would have to remember to put a negative sign here because my acceleration would be pointing in the negative direction. And that's one of those things that you often forget to do. So if you just do this, if you pick the positive direction to be in the direction of the acceleration, then your acceleration is always positive and you don't forget a minus sign somewhere. So here we see that our normal force is pushing up a little bit harder than the weight of the person. If the car was just sitting there at rest, v equals 0, the normal force would have to equal the weight of the car. But because it's moving, the normal force has to be bigger to keep it moving in a circular path. Because we know the force of gravity is not going to change. That's a fixed value. So what has to change? The normal force. The normal force is more or less because this cart has inertia. And as it comes in and pushes, it wants to go straight, but the track is curved and it hits that track and pushes into it a little bit because it has inertia, it wants to go in a straight line, and the track has to push harder on it than just holding up the weight. It has to hold up the weight plus provide the force required to keep this car moving in a circular path. So the normal force, if we're finding the normal force here, is equal to mv squared over r plus mg. It's equal to the force required to keep this object moving in a circular path, mv squared over r, plus the weight of the car. We call this the apparent weight. The real weight is mg, the force of gravity between our object and the ground. The apparent weight is how heavy the object feels. So think about this for a second. You're standing in an elevator, and when the elevator's not moving, you feel your normal weight. The apparent weight, the way your feet are pressing into the ground, is just the way they feel all the time. It's your normal weight. That's how you always feel when you're standing on the ground. If the elevator accelerates upward, the normal force from the floor on you is bigger than your weight. You feel like you're being pressed down into the ground, like you're heavier. And you are being pressed down into the ground. If you were standing on a scale, the reading would go up. It's reading the interaction between your feet and the floor. It's reading the normal force acting on you. So that's your apparent weight. Your apparent weight is really the normal force of the surface you're interacting with. And when the elevator is going up and it slows down, what does your body do? Your body has inertia. It wants to keep going. The elevator slows down underneath you, and the floor doesn't push up as hard. You feel lighter. And if you were standing on a scale, it would read lighter than your normal weight. That's your apparent weight. Your apparent weight is that feeling you get between your feet and the floor, and it's equal to the normal force. So we could go through, if we were given the velocity and the mass of our car and the radius of our circle, we could find the normal force acting on the car at this location. Let's move around and see what it looks like at point C now, with the car at the top of the loop. So now my roller coaster car is upside down, and the track is pushing on it with a normal force, and the force of gravity is still acting on it. And I say the sum of the forces in the radial direction has to equal m a centripetal. What direction do I want to be positive? What direction is the acceleration? The acceleration is toward the center of the circle. So I want that to be my positive direction. I add up my forces. I've got a normal force in the positive direction, the weight in the positive direction. That has to equal mv squared over r. My acceleration is positive, and I get the normal force is mv squared over r minus mg, because the force of gravity is providing some of this force required to keep the car moving in a circular path. So the track doesn't have to push as hard on the car here as it did at the bottom at point B. We're using the force of gravity to provide part of the centripetal force, part of the force required to keep this object moving in a circular path. Think about this for a minute. What happens if V is really, really big? The car is going really, really fast. Well, the force of gravity is not big enough to keep the car moving in a circle, so the track also has to push on it with a normal force. But if we make our velocity a little smaller, the normal force doesn't have to be as big. Gravity is providing a lot of the force required to keep it moving in a circle. And if we make our velocity a little bit smaller, what happens? Eventually, we can make our velocity small enough that our normal force goes to zero. So gravity is providing all the force needed to keep our car moving in a circular path. What happens if we go less than that? If we slow down even more? Then we spiral inward. In other words, the car falls off the track. It's not going fast enough for circular motion. So if we slow down too much, the car does this. It doesn't make it over the circular path. And the minimum speed the car has to have to make it around that loop in a circular motion occurs when the normal force goes to zero. So if we're solving for V minimum, we set the normal force equal to zero. Shall we look at one more point? Point D. Our cart's coming down here. The weight is pulling in this direction, and the normal force is pushing in this direction. And we say the sum of the forces in the radial direction is equal to ma centripetal. What direction am I choosing as my positive direction? Toward the center of the circle, the direction of the acceleration. And I get only one force now in the radial direction. And the normal force has to be mv squared over r. If I knew the mass of my cart and the velocity and the radius of this loop, we could figure out the normal force at this instant.